Momentum is the quantity of motion in a moving object. It depends on both the mass of the object and its velocity, so the equation is P equals mv, with P representing momentum. One really important property of momentum is that before and after a collision, it's conserved. So basically, in a system, the sum of the product of the mass and velocity for each component remains the same both before and after. One way to model the conservation of momentum in a system is through the use of pool balls. If you've got a moving cue ball and it strikes an inert ball of the same mass, then afterwards both balls are going to move away at a slower velocity than the initial velocity of the cue ball. The way you can set up this equation is m1v1i plus m2v2i is equal to m1b1f plus m2v2f. Because the masses are actually the same, you can just remove the mass from both sides, and because the velocity of the second ball is 0 at the start, you can actually set this up so that it simplifies to v1i is equal to v1f plus v2f, which shows why both balls have to move away slower afterwards. So, as we know, linear momentum is equal to P equals mv. There's actually an angular equivalent of this, which is L equals I times lowercase omega. What this means is that the linear momentum, L, is equal to the moment of inertia I times lowercase omega, which is the angular velocity, which, as we know, is equal to the rate of change of the angle as something moves in a circular path, which is equal to the velocity over the radius of said circle. What the moment of inertia is a property of rigid bodies. Basically, it defines the torque, which is the angular equivalent of force, that you need to achieve a desired angular acceleration. And it's determined based on the distribution of mass perpendicular to the axis of rotation. Angular momentum shares the property of linear momentum, where it's conserved in a system. So if you've got an object with a large moment of inertia that's spinning, and you were to redistribute the mass closer to the center, the angular velocity would have to go up to conserve the angular momentum, because the moment of inertia would go down. The inverse of this is also true. The conservation of angular momentum can be shown through something as simple as spinning around in your chair. If you were to stick out your arms, you would increase the moment of inertia, because you're distributing mass farther away from the axis of rotation. As you're spinning, if you pull your arms in closer to your chest, you're going to speed up, because you're decreasing your moment of inertia, so the angular velocity has to increase. Another example of how this is used is in figure skating. Another example of how the conservation of angular momentum is used is when you see figure skaters. You'll often notice that they stick their arms out or bring them in closer to their bodies in order to speed up and slow down the rate at which they're spinning. This is because they're controlling their moment of inertia in order to change the angular velocity.